Okay, so now I'm going to do question 4. And so we're going to be working in R2, and U is going to be equal to the concentration of something. Okay, so since we're in R2, it's going to have units of like amount per meter squared, so amount per area. So it's going to be amounts, so it could be kilograms, moles, whatever, per meter squared. Okay, that's not going to be so important, but I just wanted to mention it. And now we're going to have flux. The flux vector, which the components aren't going to matter so much for now, but typically I'm going to denote them P and Q. This is U moving through R2. Like the flux of U is how U is moving, or it tracks U moving through R2. So for example, if it's mainly being carried along by a vector, like a velocity vector field, like if there's a fluid is mainly being carried along by a velocity vector field, the flux is going to be equal to the concentration times the velocity vector. On the other hand, if this is the fusion process, the flux is going to be proportional to the gradient of U. We get the conservation and the and the diffusion equation from those respectively. I'm going to be concentrating on the diffusion equation today, and if we combine them, we get a diffusion convection equation. But however it's happening, F is the flux of the whatever is being concentrated, or whatever is being modeled here, and it's just how it's moving throughout R2. Okay, and what I want to do is I want to derive a differential equation that relates U and F. It's going to be very similar in principle to how we did these in one spatial dimension. The only difference is that instead of looking over an arbitrary interval, I have to look over an arbitrary domain in R2. So that being said, let's say I've got omega. This is some amoeba-like domain in R2, and the concentration of U at any time t is just going to be the integral over omega of U. Okay, so I'm assuming U is a function of x, y, and t. So let me write that explicitly up here. So U is a function of the space and time. Okay, so at any point, at any time, the amount of stuff in this domain is going to be given by this integral. Now I can take the derivative of this integral. If I take the derivative of the integral, I get m dot of t. Well, I can do similar things. I'm going to take a derivative on the outside, but because omega doesn't depend on t, and a doesn't depend on t, dA doesn't depend on t, I can pass the derivative inside the integral, and it's going to be a partial derivative, a partial t derivative of u dA. Okay, so this tells me how, like the mass in this domain, this is how the mass is changing. This is the derivative of the mass in this domain. Okay, but now the question is, like, how can the mass in here change? Well, if there's no sinks or sources, that's one of the implicit assumptions that we have here. Well, the flux, if I have again flux, I'm kind of going to represent as a field. It's a vector field. I can kind of represent it like this. And if we connect those, we get a line like this. Well, that didn't work out well. So blue doesn't seem to work well on a very clean board. Okay. At any rate, at any point, like let me look at this point right here. At any point, the flux going through that point has two components. It has a normal component and it has a tangential component. So the normal component, let's say, looks like this, and the tangential component is going to look like this. So this is the normal component. This is the normal component of the flux at that point. Okay, and that, the normal component of the flux, which we can write as F dotted with n. Notice sometimes I write an arrow on F, sometimes I don't. This is F dot n, and then the vector is times the normal vector. This is the only part of the flux that is causing whatever U modeled to be flowing outside of the domain. The tangential component doesn't make it go outside of the domain, it just kind of makes it go along the inside boundary of the domain. But it's only the normal component of the flux that makes it go out of the domain. So the total flux through this domain is we're going to go at every single point and compute this and then add them up. Okay, but that's adding up a continuous variable, and adding up a continuous variable is just an integral. So this is our conservation law. This is equal to the the line integral over the boundary of f dotted with in, but not quite, it's minus that, because it's the outward pointing normal vector, and this is how much is flowing out. If we didn't have the minus sign there, if we didn't have the minus, so since we have the outward pointing normal vector, it needs to be a minus sign here, denoting the fact that this is material flowing out. So it's kind of like, this is kind of like, just this integral here is kind of like rate out minus rate in, but the change is rate in minus rate out. But the change in mass here is really rate in minus rate out. And so if I include the minus sign, I get what it needs to be, which is rate in minus rate out. Okay, well now what I can do, if I continue this computation down here, by the divergence theorem, this is equal to the integral over omega of the divergence of f. And so what I have shown is that over any domain, sorry, I forgot my minus sign. What I have shown is that over any domain, I have the integral over omega of the t derivative of u plus the divergence of the flux dA is equal to 0. So for any u that for any quantity that satisfies a conservation law, so basically anything, there's no sources or sinks, this is true for any domain omega, and since this integral is equal to 0 for all domains, what it means is that the integrand is equal to 0. So it means the integrand, t derivative of u plus the divergence of f is equal to 0. Okay, this is just, it doesn't matter what u is, as long as it's a conserved quantity, it satisfies this. Okay, now if in addition u satisfies Fick's law, if we're looking at a diffusion situation, so u satisfies Fick's law. So in other words, the flux of u, and I'll go ahead and put an f here. See, I'm getting lazy with my arrows. So if u satisfies Fick's law, then the flux is going to be equal to minus alpha times the gradient of u. In which case this becomes the t derivative of u. Well, there's a minus sign, so it'll be minus alpha, the divergence of the gradient field. Okay, but we've already seen this, the divergence of the gradient field, this is just a Laplacian. So this is the t derivative of u minus alpha times the Laplace u is equal to 0. So this is the diffusion equation in 2 dimensions. And if the Laplacian here means 3 dimensions, like the double x, double y, double z derivatives, this would be the diffusion equation in 3 dimensions. But this is a direct analog to the diffusion equation in 1 dimension. We have the t derivative of u is equal to minus alpha, the second derivative of u. That's what Laplacian is. Laplacian is one way to think about the second derivative in the multivariable function. Okay. I think that's all that I want to say here. So let me just say one thing then about harmonic functions. I don't know if I said this in the previous video. Okay, so if I'm looking at a harmonic function, oh, you know what? Let's see. Okay, sorry. I'll do what I was about to do in the next video, but that's it for this video.